Hey everybody, welcome to the second part of the gentle introduction to functional JavaScript. I want to say thank you once again to Chet Harrison for joining us and leading us down this pathway. I know I personally got a lot of phenomenal information out of part one of this series, which if you haven't seen part one, you can check that out at watchmecode.net. Look for the Functional JS series, and you'll be able to watch that first session, as well as some additional videos that I've recorded in between then and now on currying. Today, we're going to talk about some additional topics that we didn't get to last time, and we want to kind of hopefully get to monads. That's kind of where we're trying to go at this point. But before we get started, there is one little piece of house cleaning that I want to mention that came up as a result of a couple of my other videos. A friend of mine reached out to me after I had put up this YouTube video about not taking an all or nothing approach, but really trying to take more of an incremental approach to learning things and doing new things. And I was very much talking about how I am dealing with functional JavaScript right now. And in his response to me, my friend said something to the effect of, there will come a point in time where the incremental steps are not really going to provide enough value. You're not going to get the real significant boost by taking these one steps and using these one tool in this one place. And at some point in time, you're going to have to make leaps and bounds and really get in there, diving in head first in order to get all of the value of the new tool that you're using. And so as we move through today's session, keep that perspective in mind, because I think there's a lot of value in there. While we are trying to present these tools and techniques in a way that will allow you to take one step at a time, there will come a point where you really do need to make the jump into the next piece in order to get the real value out of that. So with all of that being said, once again, I want to welcome Chet Harrison. Thanks for being here again, and let's dive in. Let's see how we can get from where we currently are to monads and composition and other great functional things.
Okay, hey everybody. Thanks, Derek. Derek gave me some good advice yesterday. He's been teaching he's been teaching a lot of different topics for a lot longer than I have. So his advice was kind of eat dessert first. Show me the money.
Yes.
So I'm going to start with an example in which we're going to use some monads, and the sort of vehicle for today's lesson is going to be pure error handling. Monads are very abstract, so they can handle a lot of different situations, and we'll cover some of the other monads that you should probably know about. But I think in the time frame that we've got, just running through some error handling will give you some tools that you can walk away with today and put into production tomorrow, or at least after some practice.
Yes, definitely.
So I've got some bins loaded with some functional code that you can try out and play and clone and get comfortable with. But the big pitch for today is the number one most important aspect of functional programming that you will get as a benefit is composition. Composition is, well, we all know that writing modules and writing decoupled code is a good thing.
Yes.
You know, you want to get it as small and granular as possible.
Right.
So functional program kind of just takes that to the extreme. It's like micro modules. So imagine, doing that to like each line of code. It sounds extreme, but it's actually possible.
Well, that's what a function is, right? I mean, a function is an encapsulation, an abstraction around the few lines of code that are in there.
Exactly. And a pure function is great because all you're concerned with is what goes into it and what are those types and what type is returned from it. It always returns something. Now, on the outer edges of your code, you will eventually get to mutations. So you'll change the DOM, you'll read a file, you'll make an AJAX request. But on the internal parts of your code, the vast majority of your code can be perfectly pure. So what does this get us? What does the promise of composition get us? It just allows us to pull out a function and plug in a new function as long as the input types and the output types match.
Okay.
That's it. So you can do this all day long without breaking your code. You can work on the internals of a function without breaking your code, as long as you return the same output type.
Oh, so it's like building an API at a functional level, and instead of an object that has methods and attributes and whatnot and a well-defined API, you have a function with an API. It's the method signature, or the function signature, I should say. It's the input type, the parameters, the output type. So that's
yeah. And when you look at functional code, you'll see those Henley-Milner function signatures as documentation on top.
Mm-hmm.
All they're concerned with is what is the types of the inputs and what is the type of the output. That's it. That tells them everything they need to know to do their job.
So that's where we see like the F parentheses X arrow something or other, those kinds of signatures.
Yeah. Mm-hmm.
Okay.
So what the Henley-Milner signatures typically look like X with an arrow to, or A arrow B arrow C. But we don't have time to discuss.
Sure. Whole different subject.
So let's jump into dessert, right?
Yes.
So error handling, it typically is kind of a disaster. It's a mess. We don't like to do it. It clutters up your code with all these try-catch blocks. And you have this temporal issue in which, if something breaks and you catch it later on, how do you unwind to the, pre-existing state so that everything is in sync? So with pure error handling, what we're going to do is take a flow. Let's just take a login flow, right? You present the user with a form. They put in a username. They put in a password. They press submit. You grab that information. You validate it. You go to a database. You grab some personalized data, and you render a screen that says, "Hello, Derek. Welcome to Watch Me Code."
Right.
So a lot of things can go wrong in that flow. You'll find in error handling, there's kind of two conditions that you have to look for. One would be you go to authenticate the user and the username and password don't match. That's what I would call terminal. You want to get right back to the user and say, hey, we don't recognize the username and password.
Right.
Other things might be form validation, right? You don't want to have a blank username and a blank password, and you get back to the user with, hey, your username's blank. And then they fill that in, and then you go, oh, what? But your password's blank too, right? You want to get through check all the fields in a form,
right,
before you get back to the user with, oh, you've goofed here, here, and here.
Right? Yeah, instead of hit first and boom, on your out. We're getting through all of this before we send all the information back.
Exactly.
Okay.
Exactly. So you want to aggregate those errors and then handle them.
Yeah.
So in a composed program, you would write that flow out. You'd write functions that say, get data from form. Maybe there would be some validation of the data. It's not blank, or it's a valid email string. And then there would be authenticate user, and then there would be go to database, look up user information, and then there would be render screen.
Okay.
And you could write those, like literally, that's the flow that we're looking for. Very easy to understand.
So do we have an example of this that you can show us?
Yeah, sure. Okay.
This is making sense in my head, but I'm always very interested in seeing the actual code.
Yeah. So Joanne, who is one of the core Marionette folks, gave me some feedback that I needed more examples.
Nice.
So anyways, all right. So let's look at this flow right here. Okay.
Oh, would you mind bumping up the font size a little?
Oh, yeah.
If you can. There we go. That's good.
Okay. So remember, composition works from bottom to top.
Right.
If you wanted to use our pipe, it would go from top to bottom, same deal.
Mm-hmm.
So here we have a function called validate form. And then we're going to pass it to clean data. And then I'm going to pass it to authentication. And then I'm going to fetch user data. And then I'm going to send an email saying, welcome to Watch Me Code or whatever it is.
Mm-hmm.
And then I'm going to log the whole process. Did it work? Did it? There errors? Are we happy?
Right.
Okay. And these little operators right here, chain and map, these are actually part of the algebraic structures that we're going to talk about that you would strap onto your monad. They're methods that you would have attached to your monad.
Okay.
That allow you to pass data from one monad to another.
Mm-hmm.
So the point of this is anywhere in this chain, I could fetch, right?
Right.
So my output right here, this is the happy path, as Scott Willashin, who I've got a link to. He's got some really good talks. And frankly, a lot of this stuff is inspired by his work. So kudos to him. Anyways, so what we see here as a result, this is a string representation of a monad we call the validation monad. Well, it's actually an applicative functor, but we'll just call it a monad for now. All right, so you have a monad, a validation, which has two children. It's got two subclasses, a success and a failure.
Okay.
So this creates something that we would call a sum type, which I think is poorly named. It should be called an or type because it's either this or that. It's either success or right. Now in here, everything was good, and we came back with this little package of data. I put it in the front of the pipe right here. I said process form. That's the name of this function right here. And I passed in Jacob. And it went through this entire chain and then wrapped everything up in a validation success and said, here's your result.
Okay.
Now, as we pass this from function to function to function, in certain cases, we wanted to get data out of one type of monad and put it into a different type of monad. Mm-hmm. And that's when we use chain. And other times, we wanted to take the data out of our monad, do a change on it, and put it back into a new of the same monad.
Okay.
So here's the analogy. Sorry, I'm a parent, so this came to me while I was changing my daughter's diaper the other day. so with a map, it's like your value is your baby. You put it inside the diaper, which is the functor. And then, when the baby has a poopy diaper, you want to pull the baby out of the functor, clean it up, but you don't put it back old functor, right? You put it into a new diaper. Right?
And how fitting that we're using the word functor right now.
There you go.
It sounds like dirty diaper language.
But then, your child grows up, becomes a teenager, right?
Yes.
And so the monad now becomes the metaphor is like clothing, and and your daughter no longer wants to wear, the princess dress. She wants to wear, some blue jeans, right? So she, gets out of one outfit and changes into a different outfit.
Okay.
So that's chain.
Yeah.
Now, what we're going to do, since we're working back, let's see what happens when things fail. Okay.
Yeah, definitely.
So here's the definitions of all the functions right here are defined right up here. So we've got validate form, clean data, authenticate, fetch user data, SAML, log status. Right. So right now, I've just hard coded in successful cases.
Okay.
In this function body, you would actually put in some logic, like, you would check to see if the username is not blank, right? And if it was, you'd pass back a failure. Now, at that point, if you fail at that step in validate form, you don't want to do all the rest of this stuff. You don't want to clean the data. You don't want to auth. You don't want to fetch the user. You don't want to send it. You want to short circuit that, right? You want to just kind of get to the end, report back to the user what you found, right?
Yeah, and this is typically where my object-oriented code starts to get really nasty and ugly, having to put in the if statements and other flow control logic to determine whether or not I should move on.
Exactly. So in this particular example, we're looking at the case where we're looking at the big steps in the process. This is not form validation. Validate form would have a sub-process, which we're going to look at in the next bin.
Okay.
But this is the case where you're not aggregating failures. You're hitting terminal failures, and you just want to get back to say, whoop, sorry, we got a problem here. So if I fail at any one of these steps, this is what it's going to look like. Okay, we had a failure here. Okay, and you can give it a payload. You can give it some sort of description like this is why it failed. And we'll see how you do that in the next bin example. But just to make the point here, let's turn that back to a success. And let's just say we fail in the fetch user data. We got a failure, okay? Now, again, we're not getting a whole lot of feedback on why we failed. But the point is, at any point, if you hit a failure in your process, it will short circuit, will pass by all the rest of the code and report back to you, we had a problem.
Okay. How does it do that? Is that being handled internally inside of the compose?
It is the beauty of a monad. And we're going to look at the implementation of the monad, which is actually trivial. In just a second, but I promise to give you dessert first. So
right.
So this is this. I just want to switch over to validation. Okay. This is the case where you do want to aggregate up a bunch of errors before you get back to the user. Okay.
Right.
So, and this one in this particular example, if things fail, we're going to get a little bit more information as to why they failed.
Yeah.
Because we are going to create a type system of all the errors that could go wrong.
Right. So a type being like, invalid email error or invalid password error or not, user not found or something like that.
Yeah. Name must not be blank. Email must not be blank.
Okay.
Invalid. So the great thing about when you're working with errors, you want to work with error types rather than strings. Strings are kind of a code smell because if you ever want to, say, internationalize your program and you haven't come up with some sort of strategy for doing that from the get-go, and you've got strings littered throughout your code, you've got just a nightmare. So if you are dealing with error types, when the error type can go to your internationalization code and say, where am I, and sub in the right language for, what message should be returned to the user. And it's good documentation. You really, from the get-go, have to think about what could go wrong and don't just, ignore it, document it. But if it's code, documentation can get out of sync, right? Code can't.
Right.
So for example, if I want to create a new error, and I run this, it's going to say, whoa, my error is not defined. Oh, wait, maybe I should come up with a new type. Now, the beauty of pure functional programs is that it won't compile.
Yeah.
Unfortunately, with JavaScript, you have to run your program and just see if it fails.
Yeah.
So that's loose typing for. But anyways, so let's see what's going on in this. Okay. I have a bunch of tests right here, and I've got a username and an email, and it's got 3 tests. The tests are name must not be blank, email must not be blank, and then I've got this fancy, nasty regular expression that I stole from Chromium that makes sure that your email is about as valid as it could be.
Yes.
this is a pretty concise, readable thing, right? I mean, these are the checks we're going to go through. And we're going to pass in a little data object with the name and the email. And then it's going to run through that, and it's going to aggregate up all of the errors. So let's look at the returns, right? On the first one, we got Ian Stewart and no email.
Right.
So the validation is going to fail, but it's going to tell us email must not be blank, and it's an invalid email. Slightly redundant, but hey, you get the point. Now, on the second one, when we put in Joanne's and a proper email address, we get a success. And here's your data. And this is important because this payload is going to be piped out of whatever this composition was, this validation flow, into the next thing down the pipe, like maybe authenticate or whatever you have in store. But if along the way anything else, in this form validation fails, when you pass this monad as the input to the next link in the chain, maybe it's authentication, it's going to say, wait, we've got a failure. I got to get back to the user. So I'm not going to do auth, and then it's going to pass it down to the get the user data call, and it's going to say, whoa, failure. I'm not going to do that. And eventually at the end of that composition is your moment to tell the user, the status of what happened. And the beauty of that is that's the moment at which you are going to check. You're going to check the status of the errors. You're going to open up that monad and you're going to say, okay, we had a failure. If it is name must not be blank, insert your IA18 and nationalized, stuff there.
Right.
Your username must not be blank. Else, if the email must not be blank, your email is blank, you get the concept. And note that these things can take payloads too. So invalid email is a monad. It's an error type, but it also has a value. So in this particular string template, we can say email, whatever it was that you typed in, is not valid. So all of that code would sit right at the end of your composition in one place. So that's the only part where you're messing with strings. And you've got all of this error code beautifully documented. So now I want to shift from, this is what this gets you. This is the value, into how this works. Okay.
Yeah, I'm seeing the composition here. I'm seeing how this is pretty slick looking in comparison to my typical flow to create the same kind of process and logic. But now I think I'm getting hung up on what is this monad thing you keep talking about, and where is it, and how is it really being used here? That's like the next question I have. Okay.
So if we go to the Fantasyland specification, which I have a link to on the repo. Here's the repo, but it's Chet Harrison, A Gentle Introduction to Functional JavaScript at my Git repo. There's links to the code that I just showed you. These are the two JS bins. This is the link to the Fantasyland specification. This is what it looks like. This is kind of an important document to get familiar with. There's a dozen of these different, what they call algebraic structures. And each adds a very simple method to your sort of your vehicle for using this stuff, your interface. Like full equals, that's not too scary. And concat, that's not terribly scary. Empty, that's a little bit foreign. We'll get to that. Map, hopefully some of you guys got to do Jafar's awesome tutorial and you're comfortable with map. Then we do apply, that's a little bit more involved. So anyways, I won't go through them all, but they're not particularly convoluted concepts. They're pretty low level. So with a monad, and a lot of these things, by the way, are sort of incremental steps into building up into a functor or a monad. You'll also hear monoids. Those are pretty nifty, and I hope to cover those too. So let's just jump into the monad because that's got the big buzzword. And
right. That's like the one thing that everybody constantly asks about, and I've tried to understand several times, but.
Right. Okay. So according to Fantasyland, the monad is a value that implements the monadic specification. Oh, a value that implements the monadic specification must also implement the applicative and chain specifications. Okay, so these things stack up, right?
Right.
You kind of peel back the onion a little bit. But anyways, I'm going to put this in code, so it's going to be nice and simple.
Yeah.
In fact, hang on one second. Okay. All right, so let's look at this validation monad, okay?
Mm-hmm.
Now, it has a parent called the validation, and it has two subclasses, success, this extends validation, and failure, okay?
Right.
Now, every monad is like a container, okay? You put a value in it, and then you have this interface that allows you to manipulate that value. And in a pure way. So there's no mutations going on.
Right. And we saw that in the last session when you showed us that bank account example where withdrawing funds from the bank account returned a new account object instead of modifying the existing one.
Right. Exactly.
Okay.
So now, the first thing you need to do when you have a monad is have some kind of factory, some kind of way to put a value into your monad. So according to the Fantasyland spec, we call this of right here.
Okay.
In Haskell, that would be called return. And I just need to kind of translate sort of like the Rosetta Stone, some of this language, because it's just going to be a lot more helpful when you're out there reading blog posts if you know that of means return. Okay. So we have a way of putting, if we say we want a validation of something, the implications of that is that we're assuming that it's a successful value, not a failure.
Okay.
So we can actually put something into a validation, and it's just going to return us a success subclass of that validation. We have some way of putting something directly into a success of, and something directly into a failure of. Because, at the end of the day, you still got to do the dirty work. You have to determine if you've got a success or a failure, and then choose which one of those, subclasses you're going to throw your value in.
Right. Oh, and so looking at line 23 and 25 there, success.prototype.of equals success.of, that works because success inherits from validation, and line 21 created the validation.of.
Well, I mean, I could actually probably yank this code and this would still work.
Oh, really?
Yeah, because success.
Oh, right. You're assigning. I'm sorry. You're assigning both. Okay, you're assigning both the prototype and on success.
So I got a static version too.
I see. I misread that code.
Yeah. So this is more of a convenience right here.
Yeah.
You'll find that there's hardcore properties that you need to satisfy the monadic interface, but then we'll start to give our monad some personality, so to speak, in order to address a specific problem. This right here is personality, right?
Right.
So this has got a very specific, okay, it's either going to work or it's not going to work. And this is some utilities that we've got in here, right? We can query, do we have a success or do we have a failure?
Okay.
It doesn't matter, because we're going to be dealing with polymorph issues here, because we've got subclasses and we're passing around a parent type, and that's good because that's what we want to think in terms of, I've got a validation. I don't know if it's a success or a failure, but I can hit, and then if it is a success, it's going to say, yes, I am. If it's a failure,
So in translating this into my own experience with object-oriented stuff, I would probably have like a validation object that would contain a value and contain, a success, true or false value based on what's passed into it and whether or not the validation was successful. But here, instead of having a single object that represents either success or failure, instead of having a single object that can represent both success and failure, we have single objects that only represent success or only represent failure.
Okay, let's be clear here, right? This is a single object that can represent both success and failure.
But the implementation,
children, the implementation of the children have to assume that, they don't know. You don't know if you're dealing with a success or failure. So this is a way of just conveniently querying them to find out, oh, are you a success or are you a failure? Because I'm just something that is looking for a validation.
Right.
Aren't we all? All right. So now to get into the requirements, this is probably the most important requirement for a monad. It's the chain function. Okay. Right. Chain differently for failure than you are for success. And I'll show you why. Okay. So this is the code of chain. This is it right here. Done. Okay. So what you're going to do is you're writing a function on your success child that takes a function as an argument right here. And then it pulls out the value from your monad, this dot value, and it runs the function on it and returns it.
Right.
Okay. So if I had a function that looked like this is called identity. And I pass that function in here and ran it on that, guess what I get back?
This dot value, right?
Exactly. I get the value. It's a getter, right?
Okay.
I just programmatically came up with this getter function. I didn't have to, attach it to the success prototype. So this is the way you would slip this value out of this particular success monad. But the contract with monads is you always want to keep them in a container, right? So the idea here is you can't just yank the value out and go home. You need to put it into a new monad.
Okay. Is that because of the composition? Because the composition that we're doing works on monads?
Exactly.
It's starting to make sense.
This is the contract that makes your code composable. Okay.
Right.
Now, remember how we had that sort of fail-fast situation in our composition chain? This is how it works, right? So if you have a failure, rather than running this logic, it just returns this. So this no op is just return this.
Oh, okay. So it just returns itself.
So you can chaining, but it's not going to do any work.
Yeah. Okay. So it's making sense.
Yeah.
Since you have a failure validation, a failure monad, you have the no operation. So every time you call chain, it's just going to keep returning the failure monad instance on up the composition.
Exactly. Straight down the pipe. Failures all the way down.
So it's not that we're exiting the workflow. It's not really a short circuit. It's just
no early return.
It's still running through the pipe top to bottom, but it's providing this is making a lot of sense.
Okay.
I have wanted to do this a countless number of times with chained promises. And I can see how I can actually get this accomplished now.
Good. All right. Now, second most important structure you want is the map. Okay. Now, a functor, just an aside here, we're pretty comfortable with functors because we've worked with arrays. Arrays are functors.
Yeah. Anything that has a map is a functor.
For the most part, yeah. So here's how you would implement map on your monad, okay? You have, and this is it, like, this one line of code right here. So take a function in, and rather than doing this chain operation.
Mm-hmm.
You're going to do the chain operation, but you're going to wrap it back up in a new instance of the same monadic type.
Right. So this in from the previous session, this is where we saw the bank account. You were to withdraw money from the bank account. You were mapping to a new instance of the bank account with a decremented balance.
Exactly. This is the new bank account or the new diaper right there.
Mm-hmm.
Okay. So with, technically with this and your of method, your free method up here, you've got a monad, but that's pretty abstract, right? I mean, it's not going to do a whole lot. So that's why we kind of endow it with a little more what I would call personality. In this case, we want to represent success and failure. So we have these subkids and they behavior that's unique to them. So if we go through this, you'll notice that a lot of the structures that we've implemented here are just no-ops.
Yeah. Because you don't want to do anything when you have this failure. You don't want to continue the process. You just want to just keep returning that failure over and over again until it gets to the very end. Exactly.
So, so there you go. There's a monad. Kind of covered a functor. But since we've got a little time, and I do want to spend a little bit more time on questions this session, because I apologize.
Definitely.
I kind of went along last time. So let's see. So let's talk about apply. Apply is probably one of the more powerful structures you're going to use.
Okay.
Because the thing that's kind of mind-blowing about a monad is we tend to think of values as, simple primitives like an integer or a string. But values in JavaScript can be code. It can be a function. So monads, you can actually drop a function into a monad. And then using this function right here, you can apply it to a value that's in a different monad.
I'm not sure I'm following you on that one.
Okay. So
I get the point of putting a value. You can put any value into a monad. And we've been previously putting, values of like a name or something. But you can also put a function into a monad, which makes sense because higher order functions, first class functions, whatever it is, you can assign a function to a variable name, and that variable can be stored inside of the monad like any other.
Right. So let's just a little example. So here's where currying really becomes critical. Okay. Oftentimes, when you're chaining these functions together, oftentimes you have this issue where you have functions that might be like binary operators. They might take two inputs, right? But when you're passing one output of a function into that takes two inputs, you got a problem, right?
Right.
So let's take a simple one. Okay. So examples on the fly.
Oh, add 1, 1.
Oh, yeah, thank you.
Not 1 + 1. There we go.
Okay. So now let's curry this, okay?
Right.
Yeah. Okay, good.
Right.
Now, let's throw this in a success monad, okay?
Okay.
Success of add.
Okay, so we've got the curried add function in the monad.
Yes. Okay.
What are we going to do with it?
So let's make a success. Let's see. Here, hang on a second. I got to assign these. const add success or add monad equals that, and then const one, or let's see, one equals success of one, and const two equals success of two. Now, what we're going to do is we're going to say const result equals add monad apply one, apply two.
Okay,
so right here we've partially applied it because it's a curried function, and we get back another function that's partially applied, and then we're going to apply two to it. And hopefully, if I've done this right, we will get result. Ta-da!
Hey, and that toString method, you've built that into the validation object.
Yeah,
to return validation success with the value.
That's a little helper function to just kind of come up with a string representation.
Right.
So again, you'll have like the required bits like chain, and map, and of, but as you personalize your monad for a specific domain, you will come up with little utilities as a convenient way of working with these things.
So scroll back down to that code you just wrote at the bottom. So this is the place where we can, well, I guess the word apply, the method name apply is really the key. We are applying a function to, or a value, applying a value to a function stored in a monad. We're
applying a value to a function.
And that function happens to be stored in a monad.
Exactly. So the reason why I did this is that you have to get comfortable with getting at your data, right? But leaving it in the monad.
Yeah. And if this is this a place where instead of, I guess I'm trying to see the real world example of this. Are we talking about the ability to create a composition that passes data through steps 1, 2, and 3, and then it applies a function at step 4, and then continues to pass data on out through after that? Or is what's the?
Yes, absolutely. Because composition is the goal, right? Composition is the goal. And you're going to come up against a bunch of situations in which you need to manipulate your data in various ways that you're comfortable with primitives, but you're dealing with monads. Okay. So let me just point this out. Okay. Concatenation. When I was writing this code where you aggregate all of the successes or failures in a form validation, I needed to, what happens oftentimes when you're working with monads, let's go back to this one right here. Let's take x equals success of 1, and then we'll just say success of success, right? And console log x.toString. Okay, so we've got a monad with a monad in it, right? And that's no different than this right here. This is a validation failure monad with an email must not be blank monad in it, and an invalid email, which is a family payload, right? So, so you're constantly dealing with like, how do I flatten, containers of containers? And so at first, that's going to be like your biggest brain damage. But once you get comfortable with these various things like map and chain, then you'll get pretty good at it. So in this particular case right here, see how the way I wrote this was a reduction when I run this code right here, I'm going to get back a validation success or failure for this case, and it's going to contain email must not be blank, or a validation failure or success for this case, and a validation failure for this case.
Right.
So if I wrap this whole thing up in a validation failure, I've got 3 levels of nesting.
Right.
So I needed to use a reduction, and I needed to use a way to concatenate all of these failures together.
Gotcha.
So that's when you implement what's called the semi-group algebraic structure. So if you go, this is
that's covered in the Fantasyland spec, right?
Exactly. And all that is just write your own version of concat, right? Right. So this is the logic for writing concatenation with this binary type, right? If both things failure, it's a failure. So we return a failure of the concatenation of those, this value and the other value, right? If one thing is a failure and the other thing is a success, it's a failure, but we only need the part that failed right here. And if both things succeed, then we've got a success. But you need to concatenate those together, right?
Gotcha.
And that's what this looks like right there.
Okay, so I think we're pretty much out of time here. I have learned an incredible amount from this session already, and I quite honestly think this is the clearest demonstration of what a monad is and how they really work that I have ever seen.
Good.
So thank you for that. That's something that I have struggled with for a long time. Let's get to some Q&A though. We've got about 13 minutes left before we need to wrap. About 15 minutes left before we need to wrap up. We did start a couple minutes late. I don't really see any Q&A underneath here, unfortunately. Does anybody in the chat room have any questions to ask us at this point? If not, maybe we can just continue on with a few more demonstrations if we have any. I think this session was so dang clear. It's such a good demonstration that I'm sure I will have questions once I start working.
What is Fantasyland? Okay, so Fantasyland is kind of a silly name, but it's got an interesting history, which I won't go into. Anyways, Fantasyland, if you go to the repo, the specification's down there at the bottom. It's a specification that outlines, this is what it looks like. It outlines the algebraic JavaScript specification, okay? These are algebraic structures. Each one of these dozen structures right here, you can strap on your particular object to qualify as being a setoid or a semi-group or a monoid or a functor and apply. So monoids are kind of fun. Since we got a little time, let me just touch on that, okay?
So before we get to that, let me ask a follow-on question to what is Fantasyland. Why are these called algebraic structures?
That's way above my pay grade, but
okay, all right, fair enough.
It has to do with category theory or type theory or something.
Gotcha. But all right. So let's go on to monoid then.
Okay, so there's some pretty simple mathematics that. Some simple laws that allow this sort of guaranteed composability. And the awesome thing with a monoid is you have a type and a binary operator that in combination can be reduced. I mean, that's essentially a monoid. So let's look at this sort of math stuff for a second. I'm going to do
share your screen again.
Share. Okay. Let's pop over to blank tab and we'll just crank up. That's a little bit big. Let's see. All right. Good old console. Okay. So look at this. 0 plus 1 equals 1. Do this. That's oh no, 0 plus 1.
You have an underscore in there.
Okay. Now 1 plus 0 equals 1. True.
Yeah.
Okay. This is called left identity, and this is called right identity. So in a monoid, you will have an element called the identity element.
Okay.
So again, this is a definition that needs a type, like an integer, and an operator. Okay. So this is a binary operator. It takes 2 inputs. Okay. So notice so this is called the identity element. Now, when you look at it in Fantasyland, the function that's going to return the identity element is called empty. Okay. Just so you got that clear. Okay. Now, that's the identity element.
Right. So in the case of integers, the identity is 0, an empty integer is 0.
Yes. And if we look at multiplication,
and also it's not in integers, it's in addition, the identity is 0, but in multiplication the identity is 1.
Exactly. So you've got a type and an operator, right? You need they go together, right?
Right.
But if you look at this, what we're really doing is define this special identity element is going to get us the ability to reduce. Okay. Because with reduce, you take the reduction function, but you've got to seed it with some type of value that's not going to screw up what you're doing, right?
Yeah. So if I'm doing a sum, an array dot reduce, and I want to add everything together, I always seed it with the value of 0 because I want it to start with 0, add the first number in the array to give me that, and then move on.
Exactly.
Okay.
Now,
so if I were doing a multiplication, I would seed it with 1 because 1 times that first number would produce
exactly.
It's making sense. All
exactly.
Right.
Now, notice this kind of looks a little bit like concatenation. What we're doing here is we're taking 2 values of the same type and we're creating 1 value of the same type. Right?
Gotcha.
Right. So that's why you get to define your own concatenation in these little, structures to suit whatever particular operation you want to do. Right.
That's making sense now.
Yeah. Because concatenation is really sort of an abstract way of saying, sum this up or, give me the product or whatever it is. So let's cover associativity, right? Associativity would be written like this. Okay. So over here, we've got left associativity and right associativity, right? It doesn't matter if we add 1 and 2 first or if we add 2 and 3 first. We're going to get the same number, which is 6. So that's another law that you need to have in place in order to have a monoid.
Okay.
And then the third we actually kind of covered is what we would call, don't think JavaScript closure. What that means is that if we take 2 inputs of the same type, we have a way of producing 1 input of the same type.
Okay.
Okay, that's it. Those 3 rules mean that you can write a reduction function.
Identity. What were the 3 rules again? There's
closure, identity, and associativity.
Identity and associativity. Okay.
And I detailed this in the repo right here. Yeah. Rule 1, closure. Rule 2, associativity. Rule 3, identity. So that's a little short run on that.
Right.
Now, one last thing before we go, unless there's like a really pressing question. Let's go to Ramda real quick. So if we go to the documentation, a lot of these things like chain, if you look at the descriptions in the documentation of chain, you'll see this little thing right here. It says dispatches to the chain method of the second argument if present. Okay. Because what that is telling you is if you pass in a monad with some fancy specific way you've written chain, and we call it, let's see. Yeah, this is a better example. Right here. Okay, so I called concat from Ramda, but Ramda
click on the line that you're talking about. I'm not sure which line.
Yeah.
Okay, there we go.
Okay, so in this particular case, each one of these, when they're resolved, is going to be a monad. It's going to be a validation monad,
right,
with some kind of payload, right? And then we're passing it to reduce as this sort of list of things that we want to process, right? So what it's going to do is it's going to use Ramda's concatenation code, which is going to defer to each one of the concatenation implementations in these particular monads.
Okay, the r.concat is going to go over each of those monads and call a concat method on that monad.
On that monad, right.
Gotcha.
And then look what we put in for our seed value, right? Our initial value.
Empty, yeah.
Empty. So let's see what success empty looks like, right? Success empty. Is right here. So on success empty, we're going to give it a success monad with an empty array in it. And the reason why I called a return a new success one is because if I called success.of, in this particular case, the implementation is going to already put it in, take the value and put it in an array inside of the monad, right? So then we'd have doubly nested arrays.
Right.
And that's it. I mean, that's a boatload of information right there.
Yeah, it's starting to make sense though. It's coming together.
Good.
So at this point, unless anyone else has any other questions, I think I've got some homework to do. Certainly to look at these examples and start working on some monads. I think.
Yes.
Oh, there is a question in the chat. What diagramming is used with functional programming? UML. I think UML is more object-oriented programming. It was really designed around objects. Although some of the UML structures, the process flow and workflow, could be used for functional programming, but a lot of UML is very specific to objects and methods and behaviors around objects.
Yeah, you'll see a lot of diagrams with nodes and arrows, directed graphs, things like that. But you would want to get into category theory to better understand that stuff, and I certainly don't. So,
right.
Start composing with monads. Try to write your own monad from scratch. Yeah. If you go to Fantasyland, up at the top, this is called the ID monad, and they've implemented here like every possible algebraic structure. Okay. It's a little, this syntax right here is a little noisy, but if you kind of think it through, you'll get it. It's just for type safety. But if you want sort of a cheat sheet of how to write this stuff, then come here and look at it, right? So let's find chain, right? Here's chain function.
Can you share your screen again?
Oh, did I not share? Okay, I'm sorry. Where's this? Oh, yeah. Okay. So let me just get you back to. Oops. So here's the Fantasyland spec. Up in the files right here, there's the id.js. Click on that. Here you have an identity monad that's defined with every single algebraic structure. Okay.
Okay.
So if you wanted to find out how to do chain, you could come down here, and you can see you just need a function that takes a function, and you return running that function on this value, right? And that's all I did really for these examples was I just lifted, bits of functionality from this, translated it into, yes. So 2015 where I could,
nice.
And that's it. So that's where you go.
All right. Wow. Thank you once again, Chet, for being here and for providing such a clear example of monads and everything that you've talked about. I want to just say to everyone who's been here with us for these 2 sessions, thanks for joining us. We are planning on at least one more session. We don't have a firm date for that yet, but it'll probably be sometime in August, I would guess, early to mid-August. And we'll send out some email announcements about that. So thank you once again, Chet, for being here to share all of this with us.
You're welcome. And on the next session, we're going to cover functional reactive programming.
Ooh, yes.
I mean, I just showed you one type of monad. You should probably learn an IO monad, which essentially is going to do some mutation, but you bottle it up in a function rather than doing the mutation. You just return the function. You say, just call me when you're ready. Mm-hmm. But that's the IO. And for async stuff, that's where functional reactive programming really kicks ass. I mean, you're going to drop promises like a hot potato when you get to FRP. So
nice.
It's going to be awesome.
All right. Thanks, everyone. And we'll see you next time.